Hello, my dear students. Now this is the start of lecture number 6 under the title Shift Keying and Multiplexing Techniques in Digital Modulation. In the previous lecture, lecture number 5, we deal with what's called digitalization, where we have studied the process of converting the analog time domain signal into a digital signal, and we considered that digitalization means discretization of the signal in both time axis and amplitude axis by using what's called sampling, quantization, and then converting it into a stream of bits by using the encoding process. Now, using our digitalized message, we are going to study how we can modulate such a message using what's called the shift keying modulation techniques. So now, please permit me to start sharing my presentation slides and start lecture number 6. I believe now you can see my presentation slides, so let's start together this journey. Okay, so based on our previous knowledge, we understand the process of modulation through having a message and a modulator. This modulator has another input, which is a carrier. Then we have what's called a modulated signal over the channel. And then we have the reverse process, which we call it the demodulation process, to re-extract the original message. In digital modulation, our message is converted from being an analog message to be a digital message in the form of a ones and zeros. We also explore together different ways in order to explore these ones and zeros using what's called line coding techniques. Now we have these ones and zeros, and we need to modulate these ones and zeros over still an analog carrier. So, as we mentioned earlier, in the carrier signal, we have 3 main parameters that can be tuned based on the message. These parameters are the amplitude of the carrier, the frequency of the carrier, and the phase of the carrier. According to this classification, we have classified our analog modulation techniques, if you remember, 2 lectures ago. When we classify our analog modulation to be an amplitude modulation AM, frequency modulation FM, or a phase modulation PM. Now, we are going to make similar classifications in the digital modulation. Additionally, later on in the next chapter, we are going to combine the amplitude modulation and the phase modulation under the name QAM, or quadrature amplitude modulation, as one of the most famous digital modulation techniques. So let's start together. First, let's start with the first and most easiest way to modulate a digital signal, which what we call the amplitude shift keying. Here we call it the binary amplitude shift keying because basically our digital signal is in the form of binary bits, ones and zeros. That's why we use the word binary. So if you remember from the basic understanding of an AM modulation from the analog perspective, the modulation process in the case of amplitude modulation is simply a multiplication process between the message and the carrier. So what we are going to do is we are going to do the same process here, but with having a message in a digital format. So by multiplying the message in a digital format with respect to an analog carrier, as you can see here, you will get out a modulated signal in a form of 2 cases. Either to have a carrier, as you can see, or you get 0. Whenever the input message is 0, then 0 multiplied by the carrier will get 0. So simply, this is 1, 0, 1, 1, 0, which is produced by multiplying the digital message by the carrier. We call this shift keying because you have an on-off carrier. Either to have a carrier, then you have a 1, or you have nothing, you have 0, then you have a 0 bit. So this is very simple like that. This is the representation, and this is the process. How we create our amplitude shift key process. The next step is again making block logic using the same classification. So we first start with the amplitude shift keying by changing the amplitude. Now we are changing the frequency. So we have what's called the frequency shift keying. In the frequency shift keying, again, I'm using the word binary because we are modulating a binary data ones and zeros. So here we have two different frequencies, what we can call it F1 and F2. If you have a 1 bit, then your carrier frequency will be F1. And if you have a 0 bit, then your carrier frequency will be F2, or vice versa, actually. So in this case, your output signal will be in this format. It's a changing frequency signal based on the nature of the input binary data you have. Here we have to consider a very important perspective related to the frequency domain or the frequency spectrum of the modulated signal. For an example, in this case, if I ask you, please estimate the bandwidth of this signal, I believe you can do it. How can you do it? How we can estimate based on our previous knowledge, how we can estimate the frequency spectrum of such a digitally modulated signal. So let's usually, let's make a very easy example. If you consider your input is a 1010 input, which is one of the cases, so simply speaking, the modulated signal will look like that. So let me first start to make these durations. So this is 1, 0, 1, 0, and so on. So this duration, we will call it TP, or the time duration for 1 bit. We already mentioned this term in our previous lecture, if you remember. Then we have a sinusoidal carry. Looks like that. So you are now interested, of course, this should be the same number of cycles per duration because it's symmetric. Again, this is due to my bad drawing. So this is a periodic signal. We can calculate its Fourier transform in a very easy manner. How we can calculate the Fourier transform? Let's start as usual. We did this actually 2 or 3 times before, if you remember, with the train of impulses, with the sampling and all this stuff. So if you have a periodic signal like that, and you would like to calculate the Fourier transform, then your first step is to consider only one period. So, okay, so this is one period. For example. And then start to write an equation to describe this period. So you will say the following. This equation is this function, which, for example, let's call it ASK of t, because simply this is modulated amplitude shift keying modulation. This is simply sine 2 pi fct whenever the t is varying from 0 to tp and 0 from tp to tp, or you can say that it's 0 otherwise. So simply what you are going to do is that you are going to calculate the Fourier transform of this signal for the one period. And then after calculating the Fourier transform for one period, you will say that, okay, this is a periodic signal, and periodicity in one domain will cause discreticity in the other domain. So you can easily estimate that bandwidth of such a prefixing. So this is a way where you can use to determine the bandwidth of one signal. Okay. Now let's turn back to this slide. So here is a formula that you can use in order to estimate the bandwidth of the signal, which is 1 plus d times s, where s here will be always considered to n, which is the number of bits, and r, which is the representation of the number of bits per sample, is 1. We have 1 bit per sample, so r equal 1 and s equals to n, where n is number of bits in 1 second. As you can see here, s is what we can call it the baud rate, or the number of samples per 1 second. So you can estimate the bandwidth here. Again, with the frequency shift keying, you can also estimate the bandwidth. Of course, here you should expect a wider bandwidth of it because you have 2 operating frequencies, f1 and f2, and we define the delta f as a difference between these 2 operating frequencies. So you can use this equation to estimate the bandwidth. Logically speaking, and also we already discussed this in more details with the AM modulation, sorry, with the analog modulation. Usually FM modulation needs more bandwidth rather than AM modulation. So this is the same case here. In the digital modulation, again, FM needs more bandwidth. But herein, actually, there is one of the very important points to consider whenever you are considering what's called the noise immunity of a digital modulation. In the AM analog modulation, your carrier envelope, it changes with respect to the message. So whenever you have an imposed noise, this imposed noise will affect the detection capabilities to reconstruct the message. However, herein, we don't have this problem because simply you have only 2 levels of the message. It's either 0 or a carrier. So whenever you have an added imposed noise over the signal, you can easily detect in the receiver. This is a true example to understand why digital modulation noise immunity is much better than the analog modulation noise immunity. In both cases, we are comparing apple to apple. We are comparing amplitude modulation to amplitude shift keying. But as you can see in the amplitude shift keying, the modulation, the noise immunity is much better than the noise immunity in the amplitude modulation. So this is the second case where we call it the binary frequency shift keying. Now we have 2 frequencies, and the frequency of the carrier change with respect to the input message. If it's 1, it has some certain frequency. If it's 0, it has a second frequency. We also have 2 types actually of the frequency shift keying. What we call it the coherent frequency shift keying, and what we call the non-coherent frequency shift keying. And this is actually, or simply, this is depends on the number of cycles with respect to the bit duration. So to illustrate it in a better manner, let's go to this example. So if you have, for example, a carrier, I will write a very trivial example just to demonstrate the idea. This is actually not a true value. So if you have a carrier equals to a C sine 2 pi, let's say 2 pi 10 t. Okay, that means the frequency of this carrier is 10. I mean, this carrier makes 10 periods per second. This is the definition of the frequency. That's right. So or the period takes 1/10 of the time. So the period takes 1/10 of a second. So it takes 6 seconds. So this is the definition. If TP, which is the time for one bit, is 1 second, then I should expect something like that. 1, 2, 3, 4, 5, 6, 7, and that's 10 to 10, and then that's all. So here, in one TP, you have an integer number of frequencies, of periods. In one TP period, you have an integer number of cycles, of periods. What if TP equals 0.3 seconds, for example? Or not 0.3, 0.35. Then you will have 3.5 periods in one TP. So now the TP will not include a clear integer of periods or of cycles from the carrier signal. So how this affects our modulated signal? So let's see. Here is the issue. For example, here we are considering, For example, here we are considering what's called a coherent modulation. As you can see, we have an integer number of cycles per TP. Here, for example, we have 1 cycle, 2 cycle, 3 and 4. And here we have 1 and 2. So we have what's called a smooth handover in this point, because now a cycle is terminated and a new cycle will start. However, in the case of a non-coherent frequency shift keying, you will have what we called previously the phase overlapping at the transition points between bits, because you don't have complete number of cycles. So, for example, you can see something like that. Because now in this TP period, you have 1, 2.5 cycle, or quarter cycle actually. So, this is half cycle, not a quarter. So this is 1, 2.5, 1, yes, 2, yes, and half. So this is what called, if you remember, the phase overlapping problem. So in the non-coherent frequency shift keying, you can have this phase overlapping problem which affect the bandwidth of the signal, if you remember. In order to guarantee that there is a coherency in the frequency modulation or frequency shift keying, you have to guarantee that this TP is n or multiple integer of TC. What is TC? Is 1 over FC. So there is a coherency between TC and TP. So for example, you have TC equal 1 second and TP equal 10 seconds. So you have 10 cycles per bit. Or you have TC equal 0.1 second and TP equal 1 second. Then we have this coherency. So this is a coherency condition. Otherwise, you will have a non-coherent frequency shift scheme with some sort of phase overlapping. So let's now continue. So now this is a frequency, binary frequency shift scheme. And let's now do the third and the final way of digital modulation using shift keying techniques, which is that binary phase shift keying. Now we are using 2 phases in order to represent the signal. And logically speaking, it makes sense to use 2 phases in an extreme manner. So if you are using a 0 phase, for example here, for representing 1 bit, it makes sense to use a 180 phase to represent a 0 bit. So you have two extreme points to increase the noise immunity. So this is the case here, while representing the ones in a zero phase, this is a blue signal, and representing 0 by 180 phase, which is a black signal, as you can see here. However, such representation will include by default what's called the phase overlapping problem again. So you increase the noise immunity, however, you also increase the bandwidth. Again, remember, we never have a free lunch. Whenever we have a one added point, you should lose something in comparison or to compensate. So this is a representation of ones and zeros in that binary phase shift key. Okay, herein we introduce the process. It's actually a very easy process. Maybe I dropped one important slide here, I think. Yes. Okay, no, I didn't drop anything. So here is very easy. If we make it here a comparison, this is the AM modulation, sorry, the amplitude shift keying modulation. So you just multiply the binary representation with the carrier. Now let's make use of our line coding techniques. What if we represent our carrier in a polar representation? If you remember these polar representations with 1 and -1. So now if you have this polar representation and multiply your binary digital signal with your carrier, you will end up with a binary phase shift key. Because 1 times the carrier will get the carrier, and -1 times the carrier will get the anti-phase, which is 180-degree phase of the carrier. So now you can easily implement the binary phase shift keying modulator using your line coding knowledge. Perfect. Okay. So maybe we did not discuss a point. I just figured it out now that we did not investigate how we can create this FM or frequency shift keying signal. Maybe this is somehow advanced for your code, but we have what's called the VCO, or voltage controlled oscillator. In the voltage controlled oscillator in the VCO, this block create an oscillating signal. I believe you already hear, maybe during this course, I believe, or maybe in previous course, you hear the word oscillator. So oscillators are these electronic signals capable of generating oscillating sinusoidal signal. In the VCO, this VCO is one of the most famous RF blocks, by the way. So in the VCO, you can create an oscillating signal with a variable frequency based on the input voltage frequency, which is typically what we need here in the frequency, here in the frequency shift key. So whenever you have a 1 voltage, you will create an oscillated signal with a frequency of 1. Whenever you have a 0 voltage, then the frequency will change. So this is typically what we do. So this is just for your information to understand how we can generate a real frequency shift keying signal. So now we consider the 3 main steps for creating a digitally modulated signal, either using amplitude shift keying, frequency shift keying, or a phase shift key. And you can understand that the main problem with this is the required bandwidth that will be much greater than the required bandwidth with the case of the analog modulation. Herein, there is another important configuration or representation that we have to study. And actually, this representation will not only affect us in this lecture, but it will also have a major contribution with the next lecture with the quadrature amplitude modulation techniques. This is what we call the Constellation diagram. What is the Constellation diagram? A Constellation diagram is a polar diagram that represents the amplitude and the phase of a signal. So I believe we already did something like that to some extent in the amplitude modulation lecture. But let's start the study. Okay. So the constellation diagram is simply a two-dimensional diagram in a polar format. So maybe you of course you studied the polar format before in maybe mathematics and other courses, but let's make a very quick flashback. So you are representing the amplitude in this direction. This is the phase. So this also represents the 0 phase. This is the 90 phase. This is the 180, and this is the 206. So, for example, if I would like to plot a constellation diagram for the binary phase shift key, I would say that okay, I have two conditions, either to have the 1 or to have the 0, and we agree that 1 will be reflected by a 0 phase carrier, and 0 will be refracted by a negative 180, not negative 180 carrier. So, and both have the same amplitude. So I will make two equally weighted points. So the distance here is AC, and the distance here also is AC, because both have the same amplitude. But I will allocate one at the 0 phase to indicate that this is the 1 bit. I will allocate another one at the 180-degree phase to indicate this is a 0 bit. So simply, this is the constellation diagram for the binary phase shift key. Using the same method, you can also plot a constellation diagram for the binary amplitude shift key. In the binary amplitude shift keying, again, you have two conditions. In the first condition, you are generating the carrier with 0 phase. So it will be typically the same like this. However, in the 0 case, you are generating nothing, which is 0, the origin point. So you can easily now understand the amplitude shift keying, the binary amplitude shift keying techniques by using simply the same constellation diagram, but with allocating the 1 on 0, especially the 0, in another place, which is the origin. So this is how constellation diagram demonstrated. Maybe it's too trivial to plot the constellation diagram for binary phase shift keying and for binary amplitude shift keying. However, in the next lecture, whenever we are dealing with the binary, sorry, with the quadrature amplitude shift keying, the QAM modulators, it will make sense to have such a constellation diagram in order to represent different amplitude, different QAM modulators. So this is the constellation diagram. I believe, or I hope that you get the message while in this slide. So this is a constellation diagram, and this is simply how it looks like whenever you have 1s and 0s. So this is a carrier, and this is a carrier with phase shift 80. So in the 1, you are directly have the carrier, as you can see here. Let me operate the pointer. So for the 1s, you have directly the carriers. For the 0, you have the anti-carrier or the counter carrier with an 180 degree. This is simply the binary phase shift. You can plot somehow the spectrum. Of course, I will not ask you to make it, but this is somehow some sort of a sinc function, and it makes sense to have it in a sinc format because it's somehow due to this rectangular boxes. I believe we already discussed this to some extent while we are dealing with sampling, if you remember. But actually, I will not ask you in specific to make this frequency spectrum, but it's good to know how it looks like and how it is represented. We also have another way of binary phase shift keying, which we call the differential phase shift keying. In the differential phase shift keying, we are using a different way to represent one and zeros. So whenever you have a zero, you have a continuous phase. So for example, let's do it here. It's 1 and then 0, as you can see. So as far as 0, so the phase will continue normally. So you continue the signal normally. So same phase as the last signal. So as you can see, so now the last signal here starts with 0 phase, so it will continue typically like the last signal. However, whenever you have a 1, you have an antiphase. So antiphase appears with 1, not with these. And you have a correlation between this bit and the previous bit, because now this bit, which is the 0 bit, is coherent. So for example, the signal starts with a phase of -180. Then in order to, or again, not -180, it starts with a phase of 180. Whenever you have a 1, then you will change the phase. So you return it back to 0. Whenever you have 0, then you have the same phase. Whenever you have 1, then you change the phase, and so on. So this is what we call that differential phase shift keying. So this is the differential phase shift keying technique. Okay. Now we are going to turn to another way or another technique in order to make a modulation technique, which was what we call the pulse modulation techniques. Now, this is actually a very important point in order to understand the difference between the shift keying techniques and the pulse modulation techniques. And in order to understand the difference between the pulse modulation technique and the shift keying technique, we have to return actually to this slide. And maybe we have to return actually back to lecture number 2, when we start understanding the main concepts of modulation. Or the question is why we are doing modulation. The main concept of doing modulation is to avoid interference through using or through converting a baseband signal into a passband signal. And whenever you go to a passband signal, you have to minimize the required bandwidth in order to increase what's called the bandwidth utilization, in order to utilize the bandwidth in the best way. And this is actually related strongly with the type of a channel you are dealing with. Because in the communications, we have actually 2 types of channels. We have what we can call the unguided channel, which is typically the wireless communication example. Whenever you are using air or any other medium as a medium for communication. And also we have what's called the guided communication. Whenever there is a dedicated channel, which is a cable, that can be an optical fiber, that can be a coaxial cable or whatever, that is linking transmitter to receive. The most famous example for a guided communication is the guided telephone network. Our telephone network, where we are transferring calls, landline calls, and where we are transferring even data over the internet, is a guided medium. Previously, it was a coaxial cable medium, and then it is transferred. It was actually a twisted burr, with a combination between a twisted burr and the coaxial cables, and now we're going into transferring it totally to be an optical fiber network. But in most cases, it's a guided, some sort of guided communication. So, in the guided communication, you have a very big advantage is that you are now own the bandwidth. You don't have the problems of bandwidth. You are the one who own the whole bandwidth. It's your channel, it's your cable. So you are not 100% restricted with bandwidth minimization. That's why you can now avoid using a sinusoidal carrier, avoid using an RF carrier in order to make a modulation. And you can send the message somehow in its raw version. This is what we are going to do in the pulse modulation techniques. So we have three famous techniques of the pulse modulation techniques. What we call the PAM, or the pulse amplitude modulation. As you can see here, this is a rectangular pulse. And the magnitude of this pulse varies with the signal. This is typically the sampling process. If you remember the natural or the flat top sampling process, this is typically the output of a natural or flat top sampling process. In this case, you don't have a carrier. You just send this stream of pulses. The amplitude of these pulses indicate the message. So in the receiver, you are going to track these amplitudes in order to construct. It seems like you only did the sampling process and you did not do any quantization or encoding process. It's one step toward digitalization. And you send the message directly to the receiver using your dedicated channel. It isn't applicable to do so whenever you are doing unguided wireless communication due to interference. But as far as it's a guided communication, then you can do it. Another example is what's called the pulse duration modulation, or the most famous name to this, which is the pulse width modulation, PWM. It's a very, very famous technique. It's used actually in very different applications. One of them is in the motor drivers and a lot of things. Herein, the amplitude of the signal or of the message is converted in the pulse duration. So if you have a very narrow pulse, then the amplitude is low. If the amplitude increases, then the pulse duration increases, as you can see here. So the duration, the message content is converted in the duration of the width, or the duration of the pulse, or the width of the pulse. And finally, we have what's called the pulse position modulation, or the PPM. Here, you have a constant tau of a pulse signal. However, its duration, its position varies depending on the message content. So in order to understand this in a better manner, let's do an example with this modulation. Okay, so let's start with the input. For example, we have any sort of input looking like that. And then you have a certain sampling frequency. For example, this is your sampling frequency. In the first case, what you are doing is very easy, actually. What you are going to do is you will keep a constant pulse with an amplitude proportional to the message. Then I'm sorry for my very bad drawing. All these impulses should have the same duration time. So this is what's called the PAM, or the pulse amplitude modulation. In the second example, you will have a variable width or a duration based on the amplitude. So the first one will be too narrow, then this will be a bit wider, and then this will be a bit wider, and then this will be like that, and then this is like that, and then this is like that, and then this is like that. So now the duration of the pulse, all of them have the same amplitude. Now the duration or the width, so what we call the pulse duration modulation or pulse width modulation. So now the duration of the pulse changes. In the third time, the position of the sample will depend on the amplitude. So for lower amplitude, you will have the position near zero. Then it will be here. 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 Then again it will be here and then here. So the duration or the position of the sample within the period indicates the message content. That's why we call it the pulse position modulation. So now, as you can see, it is a modulation because you somehow reformat your signal into different manners. However, in this case, my dear students, you are not using a carrier frequency, as you can see. Or, I would say it in another manner, your carrier frequency becomes some sort of impulses, not a sinusoidal signal. And basically, this is one of my previous questions in a previous lecture. I told you it's a bonus question, please. Why we are using sinusoidal signals as a carrier frequency? Simply because sinusoidals is the minimum bandwidth ever. Now you have a dedicated channel. You are not seeking to minimize bandwidth. Then you can send impulses. What you gain is, this is very easy to be modulated. For example, this is simply this is a flat top sampling. So just multiply the signal with a stream of impulses, and that's all. It's a one-step modulation. So you have a very easy modulator with a very large bandwidth output, but no problem because I have my channel. Similar here and similar there. So this is one of the very famous techniques where you are using impulses in order to represent your modulated signal. Now, this is the termination for part number 1. For this lecture number 6, where we deal with the shift keying techniques and pulse modulation techniques. In the next part, which will be, inshallah, the final part of this lecture, the final part before the Christmas break, we still have 2 lectures after the Christmas break. So the final part in this lecture will deal with multiplexing techniques. How we multiplex, how we combine signals together in order to effectively or using the bandwidth in a very utilized manner. This will be the content for part number 2. I hope you got interested with part number 1 and see you inshallah in part number 2. Thank you very much.